Good morning. Today we will continue our discussion on MOSFET. So, we have discussed about the circuit structure, right? Metal oxide semiconductor. This is grown on a P substrate, right? If we talk about NMOS, this is grown on a P substrate, P type, all right. So, on top of this P type, we will grow 2 N plus region. So, this N plus region will be my source and drain. So, this will be my source and drain, and the length between source and drain, this region is known as the length. Okay. The distance between the source and drain is known as the length. Due to physical lateral diffusion, okay, or the physical uncertainty of this fabrication technology, little bit of this N plus diffusion will be extended towards the source region, extended towards the channel region. So, this is known as the lateral diffusion LD. So, this is LD, this is LD. So, your effective length L effective is equal to L minus twice LD, right, and this is my W, this is my width. Okay. So, if I draw this, then this is my W and this is my L. Okay. So, this is my width, this is my length, length of the channel where the current will flow, and on top of the channel region a silicon dioxide SiO2 is grown. Okay. So, this is my SiO2, its thickness is Tox. Okay. So, you can understand between gate to body, gate to this substrate connection is known as the body or bulk. Okay. This is known as the this connection, this P substrate connection, this connection is known as the body or, right. So, between gate to bulk, as there is a oxide region, no current will flow. So, when it is in off state, between gate and body, it will behave like a oxide, right. So, what is COX? Epsilon A by T, right. So, this is epsilon SiO2, right, dielectric constant of this silicon dioxide SiO2 epsilon A by Tox. Okay. Generally, this COX is defined in terms of femtofarad per micrometer square area, which is in micrometer square. Okay. This COX, it is defined in per unit area. So, to get the total actual area of this capacitance, what you will do? Multiply COX with its area. What is the area of a MOSFET? W into L. Okay. So, we will be discussing about this later also. So, I am just giving you a hints. So, if you discuss that how this MOSFET is working, so at starting, suppose there is no gate voltage, VGS is less than how much? VTH, this is one threshold voltage. Then what is the condition? MOSFET is in cutoff. Drain current is equal to source current is equal to 0. Okay. We know 3 region, na? What are the 3 region? The current characteristics is similar to BJT. Suppose this MOSFET, this current ID. So, what is this gate current? 0. Previously we have a base current, right, but in MOSFET no gate current, this difference. So, if there is no gate current, ID and IS, they are same. In BJT we have emitter current maximum, right, here same, symmetrical. So, they looks like same. So, suppose this is my cutoff region and this axis is VDS, right, and they look similar, current characteristics is similar. Only difference is that this is my naming is just opposite. This is my linear or triode region and this is my saturation region and this is my cutoff region. And what is this value? VOV is equal to VGS minus VT. So, once VDS is greater than this is saturation. Okay. And what are these values? Defined values of VGS. This is VDS, one this axis variable is VDS, this axis variable ID and this is defined values of VGS. Now, when you just provide a voltage, so you remember this oxide. So, if you provide a positive voltage at the gate, what will happen? This charge will increase, right. So, the body will behave like the other plate and in between we have oxide, silicon dioxide and this depletion region also, right. So, what they will do, this they will try to replicate the opposite charge, okay. Or in other words, you think if I give a positive voltage at gate, in p type substrate what is the majority? Holes, right. So, holes will be repelled, holes have positive voltage, positive charge. So, what will happen? Holes will get repelled. If holes are removed, what remains there? Immovable negative ions. These ions are heavy, right. So, they cannot conduct current, right, they are fixed in the position. So, still I do not have any current, right. Now, up to which level this VGS I need to increase? Above VTH. If it is goes above VTH, then only I will get a this positive voltage, then it will attract electron. From where it will attract electron? This and this region has large source of electron and as this voltage goes up, this positive voltage will attract electron. So, electron will come up and fill the channel. So, this moment we will say that channel is inverted, because in p substrate holes supposed to be majority, but because this region and this region are n plus. So, when I am giving a sufficiently strong voltage at Vg and S is grounded, so you can tell it VGS. So, what is happening? First holes are repelled, a depletion layer is formed. Okay. So, this depletion layer also behave like a capacitance, and then even if you go further VGS, the electrons channel is formed. Okay. So, this is called the inversion layer. And now, if you put a positive potential at drain, what will happen? Drain will collect and source will as if sourcing the electron. Clear? So, as electron is flowing this direction, we will say current is flowing in this direction. This is the working principle of the MOSFET. Now, what is this threshold voltage? This VT or VGS must be greater than equal to this VTH to turn on. If it is below this, it will not be able to attract the electron. So, this VTH, its definition is like this. There is a work function, okay. This phi ms is the work function difference between gate poly and substrate, okay. At least this potential you need to provide, so that the work function difference is overcome. Then you need to overcome the barrier potential. So, this is our barrier potential value. KT by Q ln the substrate doping concentration divided by intrinsic doping concentration. Third term is this is behaving like a oxide. Now, in oxide what is the charge? Q is equal to Cv. So, how much voltage will be generated? Q by C. So, this voltage will be third term. This is, suppose the depletion charge is Q, there is a depletion region will be formed na. How many depletion ions will be there? So, that will be Q depletion. So, Q depletion by Cox. So, these three term you need to at least, this VGS need to reach at least this voltage, so that it can attract electron to conduct. So, this is our threshold voltage. What is threshold voltage? Threshold voltage is the minimum amount of gate voltage, so that the transistor turns on. And what are the values? Values is the phi ms, this is work function difference between the gate poly and the substrate, plus the barrier potential twice phi f, plus the voltage due to the charge generated, Q depletion by Cox. So, these three term will make up my threshold voltage. So, this is my depletion region when a positive voltage is applied at the gate. Now, let us, just like the BJT, let us see the what is the current equation. So, I am just writing the current expression, we will see that how it is formed. So, we know that there are three regions, right. So, one region is, this is cutoff, this is saturation, and the condition is VDS greater than VOB or VDS greater than VGS minus VTH, and this region is known as the third is triode or linear region, which is mu1 Cox W by L VGS minus VTH into VDS minus half VDS square. Condition is VDS less than VOB, and this is linear or triode. Now, there is another condition, suppose VDS is very small. So, this half VDS square we can neglect. So, this is deep linear or deep triode, this is, this half VDS we will neglect, VGS minus VTH into VDS, this is deep triode, and condition is VDS much less than twice okay. So, actually we are having three current equations. This is one extra, you do not need to worry. This third one, if you consider that VDS is very small, then you can neglect it. Okay. Square term you can neglect to 0 and the first term remains. Clear? So, first condition is VGS less than VTH, it is cut off. VDS greater than VOB, this is in saturation, and VDS less than VOB, this is in linear. Now, we know that our COX is equal to epsilon oxide by TOX, okay. And this epsilon silicon dioxide, this is epsilon r into epsilon 0, right, relative permeability into free space permeability by TOX. So, this term for silicon dioxide SiO2, it is 3.9 and free space is 8.854 into 10 to the power minus 12, and this oxide thickness is roughly how much they are giving? 4 nanometer. Okay. So, 4 nanometer, 4 into 10 to the power minus 9. So, how much it is coming roughly? So, total epsilon OX is coming as 3.45 into 10 to the power minus 11 and COX is coming at roughly 8.6 into 10 to the power minus 3. This is in unit is in meter square. If you transfer it to micrometer, then something else will come, okay. In femtofarad region it will come. So, let us whatever their values they have given, let us consider this farad per meter square. If you make this micrometer square, then it will come in femtofarad. So, total cap, that is C is equal to, I told you we need to multiply, because this is per area, you multiply with area. Okay. Suppose your area is like L is 18 micron meter and W is 0.72 micrometer. So, L is equal to 180 nano and W is equal to 720 nano. So, it will become 1.1 femtofarad. What is the unit of femto and pico? 10 to minus 12, 10 to minus. So, femto is your so you can understand how much small value of capacitor this is, because this is for integrated circuit, right. Mainly MOSFET is used to it is suitable for integrated circuit design. So, present day all the ICs they overcome the BJT, okay, because they can be more compact. Okay. So, this is one advantage why the MOSFET is quite popular. Okay. Now, let us discuss that how we have derived na current expression, that in saturation region ID is equal to half mu n COX W by L VGS minus VTH whole square. Now, this term mu n COX, we call this process transconductance. Okay. This is known as the process transconductance, and this is defined by the fabrication technology. It is a fixed parameter. Okay. You cannot change that. This is called okay. And if you multiply it with W by L, then we tell it that Kn is equal to Kn dash into W by L. So, sometimes in some book you will be see that it is written as same thing, or in some book you will be seeing that okay, same expression, these values are considered. So, let us try to understand that how this current is formed. Now, from this value, can you tell me, does this current depends on VDS? Is there any expression of VDS? No. So, it should be constant, right. So, when it reach a certain value, it is independent of VDS, right. So, this region it is dependent on VDS. The moment it reach a saturation region, you see this is constant, because this equation there is no VDS, and this region it is what, like this, na. You see this is like a this. So, what is that expression? This fourth expression. You see, if I tell this is a constant, so this is a Kn VOB into VDS. So, this Kn VOB is, if you say this is a constant, this is my M, this is my Y, this is equal to Y is equal to Mx. So, this will look like this, na. And what is the value of VDS? Less than twice VGS minus VTH, clear. So, this region is that region, right, and this region is that region, okay. You see this expression, this is my ID is equal to Kn dash VOB VDS, right. So, this is ID, this is VDS, del ID by del VDS, what is that? Transconductance GDS. If you invert it, you will get resistance. So, what is that? Del ID by del VGS, Kn VOB, and what is the resistance? 1 by Kn dash VOB. You see, this is the resistance, 1 by mu n C O x W by L VOB, and what is the value of VOB? VGS minus VTH. What is the name of VOB? Overdrive voltage. This is Kn, right, overdrive voltage. So, VOB is equal to overdrive voltage. What is the value of this? The gate voltage need to be more than the threshold voltage, so that current can flow in the channel. So, this is my triode region, this is my saturation region, and this is my complete current expression for the linear region, VGS minus VTH into VDS minus half VDS square. If VDS is very less, then we can neglect this to 0. Okay. So, why this channel is forming? Can you tell me? Suppose this is my gate, right, and this is my source end, and this is my drain end. So, this length L is starting, L is equal to 0 to, it is coming to L, right, and source voltage is at 0. So, what is this potential at this end? What is my potential? VGS, and when it is coming towards the drain side, my potential is decreasing, right, because drain potential is higher and source potential is at ground. So, at the source end, my full gate voltage is I am getting. So, my channel is maximum, right. The more I am coming to the drain side, the drain potential is fighting with this vertical gate field. So, suppose at position x, due to this drain potential, my after which voltage your channel is forming? VGS minus VTH. So, at least you need to this voltage, so that your channel is formed, right. Then at the position X, due to this drain potential, let us say Vx is coming. So, this is my effective potential na, which is forming the channel, and as this Vx is increasing and becoming VGS minus VTH, my effective channel voltage, it will become 0 here, right. VCH is 0 here, na, because VDS is maximum at this point and they are cancelling each other. Okay. But effective my channel potential is VGS minus VTH minus Vx. Vx is the potential at position X due to drain potential. Clear? So, because of that, if drain goes even higher, then this channel will move away. This is known as the pinch off. Okay, this tapering of this channel and the ending at the drain side is known as the pinch off. Oh, this is called tapered channel. Why this is happening? This is happening because of the application of VDS. Why? Because previously you have only vertical field. So, channel was, suppose you have only Vg, Vd is equal to 0, Vs is equal to 0. So, no one to stop my channel, right. Now, I am increasing my VDS. So, it will fight with this vertical field and channel will be tapered. Okay. Now, let us draw a substrate. This is my substrate, P substrate. On top of this, let us draw N plus region, N plus region. So, this is my source and this is my drain. And if I think about 3 dimension, so this is my W and this is my L. On top of this, let us grow a oxide region. Okay. On top of this oxide region, let us grow a polysilicon which is having large conductivity and it is behaving like the metal connections, metal oxide semiconductor. So, this polysilicon or poly is suitable for fabrication over silicon dioxide. So, poly is largely used. Okay. So, you can think this is as the metal. Okay. So, this is our, say this is our 3 dimensional view. So, this is my drain, this is my gate and this is my source. Okay. Now, in this channel, this is my channel, right, this is my source region and this is my drain region, and say this is my channel. On top of this channel I have a oxide. So, in this channel let us think that I have a unit chunk, unit volume of a unit area of a electron. Okay. In this, if you have a positive gate voltage, then what will happen? Suppose your channel has already formed. Now, you are providing a drain potential, so that this electron is attracted towards this direction, right. So, this unit electron area or chunk, let us consider that this is moving towards this direction because of a application of a positive drain potential, right. So, what is this? Suppose this charge per unit length. Okay. Let us define this charge per unit length as Q or QD. Okay. This QD is my charge per L. Okay. In COX, what is my charge? Q is equal to CV, you know, right. What is your C? COX, right, and this COX is per area. So, if you want to get charge per length, you need to multiply this into W, because L is divided. So, we are not multiplying with L, getting my point. This is cap per area. So, to get the total cap, we need to multiply it with W by L, W into L, but this is my, I have to divide by L, so L will not there. Okay. So, this is COX into W, right. Next term is V. At position X, suppose this position is at X and this is VDS. So, what I told, what will be the effective voltage to form this channel? VGS minus VTH minus Vx. This Vx term is extra coming because of this. So, if I want to make a channel, what will be my effective potential at position X? Suppose this is L is equal to 0 and L is equal to L, and at some unknown position X, my effective voltage is VGS minus VTH minus Vx. Okay. So, this is my charge per length. Okay. Next, I want current. What is current? I is equal to Q by T, right. I is equal to Q by T. Okay. And you see, this Q is per L, right. So, if I want a total current, I should have I have to multiply it with L, na. So, this distance is say x. So, what is x by t? Distance by time is equal to velocity, right. This q is my charge per length. So, I need to multiply with length by time, so that I can get a current. So, let us say velocity of this electron chunk is small v. Okay. This electron is moving, because this is moving because of this lateral field, right. This is a positive potential, so this will move. So, this is moving at a velocity v, and we know velocity due to electric field E, if there is an electric field and the mobility of the electron is mu n. So, it will be mu n into E. E is my electric field and mu n is my mobility of electron. Okay. So, this velocity is equal to mobility into electric field, and I know electric field is equal to voltage by distance. So, mu n, my voltage is at position x is Vx, by say dx. So, my current become now Id is equal to Cux W into this voltage into this. So, this Id if I want to get the total current, I have to integrate from L is equal to 0 to L Id, and this dx I will multiply with this side, okay, is equal to what remains mu n Cux W VOV minus Vx into this is dVx. This is dVx by dx. This electric field is dVx by dx, and I will integrate it over L is equal to 0. What is Vds? 0, and L is equal to L. This is Vds. So, this side it becomes Id L. This side it becomes, this is constant, this first term is constant, mu n Cux W, and this VOB term there is no Vx. So, it will become VOB into Vx. This value will become Vds minus Vx square by 2, Vx we put Vx is equal to Vds. So, your total current Id becomes mu n Cux W by L Vgs minus Vth into Vds minus half. So, this is my complete current equation. You cross check it again and you follow step by step. So, first step is you find Q. What is Q? Charge per unit length. So, Cux into W and effective voltage V. What is effective voltage? VOV minus Vx. Why Vx? Because due to Vds at position x, some voltage will come, that voltage is Vx, right. Next is you multiply this with velocity. What is velocity? Mu n into E. What is E? Mu n into d of Vx by dx. Okay. So, you will get I is equal to Q into V. Then you integrate this from L is equal to 0 to L, and in voltage side it will become 0 to Vds. So, this L term will come, W by L, this will come, and in this expression suppose you put Vds is equal to VOV. So, what will happen? This will become VOV square minus half VOV square. So, the expression will come half mu n Cux W by L Vgs minus Vt whole square, the saturation current. So, this is how to derive the current. Now, if we just draw this Id is equal to half mu n Cux W by L Vgs minus Vth whole square, this will form a parabola like characteristics, but this is, so at this so here it is stopping and get flat because there is no this expression this when you are plotting this, after this saturation in ideal equation just like the early effect, if we neglect the early effect, this is flat, right. So, this flat is coming due to this. Okay. Now, why this is increasing then? Can you tell me why this is increasing? It is supposed to be like this, right, ideally, but it is in reality it will increase, and if we extend this will cross a voltage that is known as the early voltage VA. VA is equal to 1 by lambda. Okay, lambda is channel length modulation. Can you tell me why this increase in current? What is exactly happening? You see, when I increase my VDS, what is happening? As if the channel is moving away, right. So, your L is actually decreasing and your I is W by L. So, if your L is reducing because of higher VDS, so your current supposed to be increase, clear, because your I is equal to proportional to some constant into W by L. So, if you try to reduce this L, if you divide by less value, this value will increase, na. So, this is known as the channel length modulation effect. Channel length modulation means as if channel is getting changing, length is changing. So, if length is changing, length is reducing, my I should increase, okay. And this is actually happening due to the early effect, and this lambda is there. So, 1 plus lambda VDS we will multiply. I told you there is no variable of VDS, original current equation, that is half mu n Cux W by L VGS minus VTs whole square, no VDS. So, it should be flat, but now 1 plus lambda VDS term is there. So, with VDS this term will increase and this current will. So, this is my complete current equation considering the channel length modulation effect. Okay. So, let us stop here. So, what we discussed today? We discussed MOSFET structure as well as the how the current expression to derive, how to derive the current expression.